Hello everyone, welcome back to the AI Foundation Learning, where we dive deep into the fascinating world of artificial intelligence. In today's video, we'll be exploring the fundamentals of deep learning. Whether you're a beginner or a seasoned professional, this video will provide you with a clear and comprehensive understanding of deep learning concepts. So let's get started. First, let's start with the basics. Deep learning is a subset of machine learning that focuses on neural networks with many layers. These deep neural networks attempt to mimic the human brain's ability to learn from vast amounts of data. But what exactly are neural networks and how do they work? Let's break it down. Neural networks are composed of layers of interconnected nodes or neurons which process data. Each neuron receives input, processes it, and passes it to the next layer. The basic structure includes one input layer. This layer receives the initial data. Two hidden layers. These layers perform computations and extract features from the data. 3. Output layer. This layer produces the final prediction or classification. Now, let's dive deeper into each component to understand how they contribute to the learning process. The input layer is where the data enters the neural network. For example, in image recognition, the pixels of an image serve as the input data. Each neuron in this layer represents a feature or attribute of the input data. The hidden layers are the core of the neural network. These layers perform complex computations to extract features and patterns from the data. Each neuron in a hidden layer takes inputs from the previous layer, applies a mathematical operation, often a weighted sum followed by an activation function, and passes the result to the next layer. Common activation functions include relu, sigmoid, and tan, which introduce nonlinearity into the network, enabling it to learn complex patterns. The output layer produces the network's final output. In a classification task, this layer might output probabilities for each class. For instance, in an image recognition task, the output layer might indicate the likelihood of the image belonging to various categories like cat, dog, or car. Next, let's discuss how neural networks learn from data through a process called training. Training a neural network involves 3 key steps. 1. Forward propagation. Data moves through the network from the input layer to the output layer, generating predictions. 2. Loss calculation. The network's predictions are compared to the actual labels using a loss function, which measures the difference between the predicted and actual values. 3. Backward propagation. The network adjusts its weights based on the loss using an optimization algorithm like gradient descent. This process is repeated iteratively to minimize the loss and improve the network's accuracy. To make this process more concrete, let's walk through an example of training a neural network for image recognition. Imagine we're training a neural network to recognize handwritten digits. Our dataset consists of images of digits from 0 to 9, each labeled with the correct number. 1. Forward propagation. The pixel values of an image are fed into the input layer. The data passes through the hidden layers where features like edges and shapes are extracted. 2. Loss calculation. The output layer produces probabilities for each digit. We compare these probabilities to the actual label using a loss function like cross-entropy loss. 3. Backward propagation. The network's weights are adjusted to reduce the loss. This process is repeated for multiple epochs until the network achieves high accuracy in recognizing the digits. Deep learning is powered by various algorithms, each designed for specific tasks. Let's highlight some of the most important deep learning algorithms and their applications. Here are some key deep learning algorithms you should know. 1. Convolutional neural networks, CNNs. Primarily used for image-related tasks, CNNs are designed to automatically and adaptively learn spatial hierarchies of features. For example, they power applications like facial recognition and medical image analysis. 2. Recurrent neural networks, RNNs, ideal for sequential data. RNNs are used in natural language processing and time series prediction. They excel at tasks such as language translation and speech recognition. A simple example is predicting the next word in a sentence. 3. Long short-term memory networks, LSTMs. A special type of RNN, LSTMs are capable of learning long-term dependencies, making them useful for tasks like text generation and sentiment analysis. 4. Generative adversarial networks, GANs. GANs consist of 2 networks, a generator and a discriminator that compete with each other. They are used for generating realistic images, videos, and even audio. For instance, GANs can create highly realistic images of people who don't exist. 5. Autoencoders. Used for unsupervised learning, autoencoders learn efficient representations of data, often for the purpose of dimensionality reduction or feature learning. An interesting application is image denoising. Deep learning has achieved remarkable success across various applications. Let's explore some real-world examples. Deep learning is transforming industries and powering innovations in numerous fields. 1. Computer vision. Deep learning models excel at tasks like image recognition, object detection, and facial recognition. They're used in applications ranging from autonomous vehicles to medical imaging. 2. Natural language processing. Deep learning enables machines to understand and generate human language. Applications include language translation, sentiment analysis, and chatbots. 3. Speech recognition. Deep learning models can transcribe spoken language into text with high accuracy, powering virtual assistants like Siri and Alexa. 4. Recommendation systems. Deep learning enhances the accuracy of recommendation engines used by platforms like Netflix and Amazon, providing personalized content to users. While deep learning offers immense potential, it also comes with challenges and considerations. Some of the key challenges include: 1. Data requirements. Deep learning models require large amounts of labeled data for training, which can be difficult and expensive to obtain. 2. Computational resources. Training deep neural networks demands significant computational power, often requiring specialized hardware like GPUs. 3. Interpretability. Deep learning models are often considered black boxes due to their complexity, making it hard to understand how they make decisions. 4. Overfitting. Models can sometimes perform well on training data but poorly on new, unseen data. Techniques like regularization and dropout are used to mitigate this issue. In conclusion, deep learning is a powerful and transformative technology at the heart of many AI applications. By understanding the fundamentals, you can appreciate how these models work and the potential they hold for the future. Looking ahead, the future of deep learning is incredibly promising. We can expect continued advancements in model architectures, improved efficiency, and broader adoption across various sectors. The possibilities are endless, and we're just beginning to unlock the potential of deep learning. That's it for today's deep dive into the fundamentals of deep learning. I hope you found this video insightful and now have a better understanding of how neural networks work and the algorithms that drive them. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more AI-related content. Thanks for watching, and see you in the next G video.